This lecture will be a very simple lecture, particularly when we have already seen the step response of second order control systems. We already know what is the transfer function of a standard second order control system, and also since we have taken the impulse signal as the input, the Laplace transform of the input signal is equal to 1, so that the Laplace transform of the output becomes the transfer function itself. Now we are just going to see what is the rough output profile for different cases of the systems. You should pause the video and try to find the answer yourself. First case is of undamped system when the value of zeta is equal to 0. Laplace transform of the output will simply become omega n square divided by s square plus omega n square. After taking inverse Laplace transform, we will get the output signal in time domain to be equal to omega n multiplied by sin omega t multiplied by unit step signal. A rough output profile is shown on the screen. As can be seen, the output is a pure sinusoidal signal with amplitude omega n. The second case is when the system is underdamped system. The first step is actually the most important step in the process of converting signal from frequency domain to time domain, which is the rearrangement of the denominator. After that, we will multiply and divide under root 1 minus zeta square in numerator and denominator. After little bit of rearrangement and taking inverse Laplace transform, we will get output signal in time domain to be equal to omega n divided by under root of 1 minus zeta square multiplied by Euler's number raised to the exponential minus zeta omega t multiplied by sine of damped frequency multiplied by time t. The whole expression we multiplied by unit step signal. In this case, the oscillations will be damped and the output profile will eventually die out to 0. The third case is when the system is critically damped system. After putting the value of zeta equal to 1, we will get the Laplace transform of the output equal to omega n square divided by s plus omega n raised to the power 2. Taking inverse Laplace transform, we can easily find the output in time domain to be equal to omega n square multiplied by time t multiplied by Euler's number raised to the power omega n t multiplied by unit step signal. The output in this case will first increase and then it will begin to decrease. The fourth case is of overdamped system. We know the roots of the denominator will be in the form minus zeta omega n plus minus omega n multiplied by under root of zeta square minus 1. The output in this case will be in the form of a multiplied by Euler's number raised to the power s1t plus v multiplied by Euler's number raised to the power s2t. The whole expression we multiplied by unit step signal. A and b are coefficients, the value of which can easily be found by using Heaviside residue theorem. Now let us assume S1 is the dominant pole. So the second term in the output is the term which is because of the insignificant pole and will die out earlier, such that the response will be primarily due to the first term in the output expression. From Heaviside theorem, we can find the value of constant A, which will come out to be equal to omega n divided by 2 under root of zeta square minus 1. The output will come out approximately to be equal to omega n divided by 2 multiplied by under root of zeta square minus 1 multiplied by Euler's number raised to the exponential s1t multiplied by unit step signal. The output in this case will approximately look like a decaying function. You should also give a look to the short notes which I have attached in the video description. You may find few other points which don't need any explanation as they are self-explanatory in themselves.